Oh, good. Okay.
Touch anything.
Finally. Okay.
Okay, sorry.
The connection's a little. This is
Our last speaker for the afternoon session is, don't touch this. Yeah, you can't touch the HDMI connection. It's a bad technology. So if someone's trying to improve solid state, this is...
Okay, back off.
Okay, I'll just please begin.
Sure, yeah. Good afternoon, everyone. My name is J Ouyang. I'm currently a visiting professor at Honda College of the City University of New York. And first of all, I'd like to thank the chairman and the organizer for giving me this opportunity to talk about my collaborative work with my host, Professor Ren, at the physics department of Honda College. So, title of the talk is demonstration of ultra-high recyclable energy densities in domain-engineered ferroelectric films. So, first of all, I'm a mature scientist, so I would like to give a general background about how to design ferroelectric thin films, just to give you a general background. Then talk about high-energy density dielectric capacitors, why they're important, and give you a specific way of designing them by utilizing the polydomain structures that are usually formed in epitaxial ferroelectric films. Then I'll give you my example. My model system is barium zirconium titanate. It's 20% doped in barium titanate matrix, so 20% zirconium, 80% titanium. And how I achieved a mix of competing polydomain structures by phase engineering and strength tuning. So that's the design point. Then I'll give you the experiment data, structural analysis for XRD, TEM, second harmonic generation, and also electric characterization results, PV, CV, and CF results. Then from the PV, actually, you can get the energy storage density and also the efficiency. As conclusion, I'll compare the performance of my BZT thin film capacitors with some of the top performers in the field. So here's the film that you grow on a substrate. So obviously, you need a substrate to support it and also for integration purpose. And you will have an interface between the film and substrate. And the film is strained by the substrate. You're going to have strain effect. And also the film is usually have some defects. For example, for perovskites, oxygen vacancy is probably the most important one. So knowing this general background, then for perovskite ferroelectrics, you can design from 3 different major approaches. First, about interface. Interface, of course, is a gate that controls the charge transport. And sometimes when you have multilayer thin films, you're going to utilize the interlayer coupling to achieve some of the functionalities that you won't get in single layer thin films. And the strain is the most important effect that substrate impose on the film. You can tune the property of the current phase, or you can achieve some new phases, so-called strain-stabilized phases. In thin films, there's a lot of examples in bismuth ferrite oxide films. And also, you can tune the polydomain structures. And also in non-epitaxial films, for example, the polycrystalline thin films, you can tune the grain structures by utilizing the strain. And the third aspect is the chemical control, the stoichiometric control of the thin film. Basically, if you grow an epitaxial film, but you don't do good chemistry, so you will get leaky dielectrics. So epitaxial doesn't guarantee you a good film. So, but I won't touch this point, but just give you a general background about design of a ferroelectric thin film. So here I'm going to mostly talk about the PV hysteresis. So here is a very classic PV hysteresis. For example, if you have a single domain tetragonal film, your polarization is aligned with the electric field, so there's not too much you can change. Your remnant polarization is about the same, so slightly slower than saturated polarization. So this is very good for memory, as we all know. But if you look at this area, the green area, which means you go up to PS and go back, The green area is the part of energy that you can recycle. The yellow area within the loop is all loss. So that's from the dielectric capacitor point of view. So if you want to change this hysteresis loop, let's say we still make the film homogeneous, a single phase, single domain film. You want to get some type of different PV loop. You can change the phase, right? You can change it from tetragonal to rhombohedral. So now you apply a 001 electric field. Eventually your polarization can align more with the electric field, so you have a big difference between the remnant and the saturated polarization. That's the intrinsic way to do it. But there's another way, I think it's well known in the field, that you can utilize an interface layer, so-called space charge layer or dead layer, to tune your ferroelectric PV loop from a square-shaped loop to a more slim loop. That's well known in the field. So here, I would propose a way of introducing inhomogeneity in the thin film. So I'm not having a single phase, single domain film anymore. Instead, I can have relaxer, polar nano regions, or we can engineer the grain in polycrystalline film, or the domain structure in epitaxial film. You can see here's an example. If you have a single domain to start with, so you can, of course, you can change it substantially by applying a field. So this feature, the characteristic for this loop is very easy to saturate, but very difficult to discharge, right? It's difficult to make the remnant polarization to disappear. But if you have a polydomain structure which has a head-to-tail configuration of domains, and this polarization is canted to the applied field, so in the remnant state, you will have apparent zero polarization to begin with. And when you charge this film, of course, one of the domain will be favored, one set of the domain will be favored, but this is at the cost of removing the domain interface. So it's very difficult to be saturated. At the same time, if you discharge, because the head-to-tail remnant configuration is stable, you can get close to zero remnant polarization. So this kind of structure is very good from a dielectric capacitor point of view. So let's go back a little bit about the dielectric. We know the linear dielectric, for example, alumina polymer, linear polymer, the energy density stored in a linear dielectric capacitor is just the area between the dielectric displacement and electric field. It's linear, right? You can use a very simple equation to calculate that. But for nonlinear dielectric, for example, ferroelectric or antiferroelectric, they're different, right? So the key, like I just mentioned, to improve the recyclable energy, that's the area outside of the loop, you're gonna have a very small remnant polarization and a very large saturated polarization to achieve that. At the same time, another key parameter you need to consider in the design is to improve the applicable electric field as large as possible, because this energy that you can store is only in proportion with the dielectric constant, but it's in proportion with the square of the largest field that you can apply to this dielectric capacitor. So we can have different ways to design it, like I just mentioned. We need to switch from a square-shaped PV loop into a slim, tilted PPE loop. We can design it by grain structure, nano-grain structure. We can design it by interface. By utilizing this interface, we can use relaxers, or we can utilize the domain structure. And this is what I'm going to talk today. So technical background, this is a new paper just published last year about all different kinds of dielectric capacitors. So the y-axis is the energy density, and the x-axis is all different technologies. You can see some familiar face there. You can have the multi-layer ceramic capacitor, nanodielectrics, and this is developed by Murata, that's a Japanese company. And you can have also have antiferroelectric composites. So the highest that reported so far is somewhere near the 30 joule per cubic centimeter. But in my work, I'm going to show you that by properly engineer the domain structure in the barium titanium oxide-based Fe film, you can achieve energy density several times higher than the current record. So for application of this dielectric capacitor, of course, we know its major application is power electronics and for power conditioning. Therefore, because they're so fast, if you can improve the energy density, you can use it in some future technology, for example, hybrid or electric cars as an inverter, capacitor, or you can invent some hybrid batteries or high-speed energy storage units. So a little bit background about the elastic domains. Dr. Roybert gave a very nice background, so I'm not going to spend too much time. But here, we know that the elastic energy, as you grow a strand film on substrate, it increases with film thickness. So very thin film, of course, you don't like to have interfaces. It's a strand uniformly across in the bark. But when you grow film above some critical value, you're going to form polydomain as a way to relax the epitaxial stress energy. As you grow film even thicker, you're going to form a higher order or so-called hierarchical polydomains. It's kind of like a fishbone domains. I believe a lot of earlier presenters already showed some nice pictures of this second order or higher order polydomain structure. So you're basically trading the residue elastic strain energy. You're reducing the elastic strain energy at the cost of extra energy associated with creating extra interfaces. So for these films, the second order or higher order films, these polydomain films seems like they're not very useful for memory application because the domains that usually aligned with polarization head to tail. The remnant polarization is likely to be close to 0, and the overall apparent polarization actually is unwilling to align with the electric field because of the interaction between the domains. So this is good for one type of technology, but maybe not. So for dielectric capacitors, this could be an ideal candidate. So again, I just zoom in the picture I showed you earlier a little bit. If you begin with a polydomain with a head-to-tail configuration, so the apparent remnant polarization is close to 0, and when you apply a field, so you're going to change the polydomain structure into close to a single domain structure. But if you discharge it, because these domains are their equivalent and remnant, they would like to stay in this head-to-tail configuration, you can discharge most of the energy that you initially put in the ferroelectric capacitor. So that's the idea from domain engineering point of view. We would like to have this kind of polydomain structure to begin with. So if we can have, instead of this so-called first order, we can create even a step further, we can create a second order. So this is the domain that I show you here. But if you can have even finer domain structures in these first order domains, that could be even better. Because as you go smaller, this domain structure, so-called nano domain structure, can become very adaptive to the change of field. So in order to create such a polydomain structure, I start from scratch with the barium titanate. We know barium titanate in the undoped state is a very stable tetragonal. I try to do some polydomain film out of only single phase, only the barium titanate, but I always get the polydomain of tetragonal. It proved to be not too much use for the dielectric capacitor applications because they're very difficult to switch, 90-degree domains, as you all well know. So I try to make it a rhombohedral, like I said, allow the polarization have a certain degree with the applied field. So in this case, I dope it with a little bit larger iron zirconium. It's larger than titanium. So you drag the stable phase from tetragonal to orthorhombic until you go to the rhombohedral. Until you hit 25 or higher, you get a relaxer. I don't want to go to that side. So I pick something at 20%. We know it's rhombohedral in the bark. But at the same time, if you grow this composition, a film of this composition on a substrate, the substrate, the symmetrical implant compressive stress will stabilize the tetragonal phase, as we all know in the classic case of bismuth ferrite. So if we control a bulk stable phase rhombohedral, but we grow it on a cubic substrate, so I can stabilize my tetragonal phase. In this case, I have possibilities of creating two types of polydomains. One is when the film is thin and the residual strain is very high, I can expect a tetragonal rhombohedral mixed phase, just like in the case of bismuth ferrite. But when the film is thick or the strain is relaxed, I can expect some sort of rhombohedral dominant kind of microstructure, and hopefully I can have some of the higher order polydomains. So that requires that I grow the film really thick, not a few hundred, but into the micrometer level. So that's what we did experimentally. Before I show you any experiment data, I just elaborate a little bit of my point here. So you can see here, this is free energy as a function of misfit strain, right? I use the reference state is rhombohedral. You can see when there's no strain, the minimum is here. Then this green curve is tetragonal. Of course, it's higher. The ground state is higher. But when you put it on a substrate, there's some certain misfit range that the mixed phase is become more stable, right? I don't need to say more about it. People already know it in bismuth ferrite case. But you can see when the misfit strain is higher, it's close to the self-strain of the tetragonal phase. So the dominant polydomain structure will be a tetragonal rhombohedral mixed phase, just like in the case of bismuth ferrite. In this case, you have a finite remnant polarization, but you probably can harvest a little bit more of energy density because you apply the electric field, you're going to change one phase into the other. That costs you extra electric energy. But if you have a very thick film, you're going to have a dominant rhombohedral structure, hopefully, if we can have this hierarchical polydomain. So in this case, your apparent polarization close to 0. And this polydomain structure ideally can have close to 100% charge-discharge efficiency, like I just described in the beginning. So in this case, not only we need to grow film on different thickness, but we also tune the film misfit by growing them on different substrate. So this is one of the typical XRD results. I show you the XRD results of this BZT film grown epitaxially on strontium titanate. You can see very nicely all these Z0L peaks. And you can see actually there are 2 peaks on the BZT. So one is tetragonal, one is rhombohedral. And we did 5 scans of both peaks, just showing you nice 4 peaks, indicating the epitaxy quality of the film. And we did some very intensive TEM work. We checked all the 4 different thicknesses from 350, 700, 1.4 micrometer. The thickest is 1.8. Here I'm showing you just as an example. This film is about 700, this is 200, the scale bar is 200. So this is about 700 nanometer. You can see all these column-like structures. And then when you zoom in, you can see all this nicely oriented zigzag kind of domain structure with a 45 degree with respect to the growth direction. So by just looking at the crystallography, you can tell all these are the higher order domain structure of rhombohedral. And then we did some select area diffraction work. So near the interface, that's the C, the circle C, we found that, of course, we found the substrate, we found the bottom electrode, and we also found tetragonal and the rhombohedral spots. And the rhombohedral spots, actually, when you grow more into the film bark, which is D here, you can see the tetragonal peak, actually, the tetragonal spots disappeared, but you have some very fine structure in the rhombohedral diffraction spot, and eventually we figured out this is because you have 2 sets of rhombohedral microdomains which grow from the bottom interface up until the surface of the field. So with this information, we did some second harmonic generation study. By the way, we have very intensive second harmonic generation results presented in a poster, and feel free to take a look. And we also have some nice acoustic phonon results there. But here, basically we took the depolarization second harmonic generation signal, and the intensity of this signal indicates the volume ratio of rhombohedral. The higher the intensity, the more rhombohedral phase you have. So we did, I show you one on the left is the SSG spectrum for the thinnest film, 350 nanometer. And this one is for the thickest one. You can see the intensity actually grow almost twice. So based on the TEM, XRD, and the second harmonic results, I can show you the schematic of the structure. So when the film is thin, dominant structure is T and R. When the film grows thicker, you have dominant rhombohedral structure, and you have some spots. When there's a highly stressed region, you can have tetragonal phase there to relax the growth stress. So that's the structure that we envision from the experimental results. Here, just quickly show you the experimental results. So these loops are for the thin film. You can see very slim, but still you can see some loss there. And this film has an efficiency of 85 to 90. But when you grow really thick, you almost think you're looking at a linear dielectric. Actually, they're not. If I enlarge them, you can still see the ferroelectric loop, but they're very, very slim. So the energy density, of course, the highest is for the thinner film, which you can apply higher field, is about 170 joule per cubic centimeter. And the thicker film actually have efficiency close to 100. Actually, the best record we got is 96% of the film grown strontium titanate. And here I show you the low dielectric loss of this nano polydomain film. This is a film grown LAO. It's about 2 micrometer. We apply basically 400 volts on the film. You can see the loss stays low up to the megavolts per centimeter level. That's good quality film. And we also did temperature stability study. We cooled down the film down to minus 170 and heat it up to 200 degrees C. You can see the energy change within about 10%. Efficiency, eventually, there's no change. It's all about 90%. And here's the dielectric dispersion. And you can see, very surprisingly, very stable dielectric constant. And we propose a mechanism of ultra-adaptable nanodomain, so the nanodomain can really respond to the field change when comparing with the large-scale domains. And here is the cycling performance. We cycle the film up to 100 million times. You can see here is the change in polarization. So you can see the maximum polarization actually only changed by 20%. From after 100 million times, the maximum polarization becomes 80% of the initial one. But what changes most is the remnant. It becomes only 40% of the initial. So with this information, you can calculate the energy change, the energy density change, and the efficiency. Efficiency actually slightly increases, more close to 100% after 100 million times cycling. And the energy density actually decreased about 20%. I think that's a very good record when you think about chemical supercapacitors. Usually they cannot cycle this many times. So the hypothesis here is the strength stabilized T phase, when cycled 100 million times, they transform to the box stable phase, R phase. So we have some more results which support our hypothesis. And we have some nice work actually in progress, trying to explain the cycling performance, comparing the performance of some fresh and some fatigue capacitors. And here just put you in the perspective how this compares with some of the top performers. Dielectric polymer, they're good in dielectric strength, but they're low in dielectric constant. That's why they're in this corner. And some of the lead-based ceramic, the high dielectric constant, but they cannot induce high voltage. But this blue line is my BZT thin film capacitors. It's good both in dielectric constant and the dielectric strength. And if you put in this famous chart, you're always looking for electric device with both high energy density and high power density, and this is where this work is at. So with that, I'm going to conclude my talk here. Last year, I actually presented some work of utilizing interface coupling. I grow a bilayer BTO BFO film. I show that I can significantly improve the energy density of a BTO, almost 60%. And this year, I show you that I can engineer the polydomain structure in BZT films to achieve very slim hysteresis with very high energy density. And in the future, actually, I'm going to show you, hopefully, if I'm lucky enough, I present again next year of how to utilize nano-gray engineering to achieve the same kind of PV curves. With that, I thank you and I welcome your questions.
Okay. So James had to run and catch his plane, so I'm taking his place. I think at this point we only have time maybe for 2 quick questions. Okay.
Nice talk. Just whether, I'm not sure if I understood, why did you put 20% of zirconium? It's to approach rhombohedral and tetragonal energies together?
Let me just show you here. So, here, sorry. You can see when you dope with zirconium, actually you change the ground state from tetragonal to rhombohedral, right? Okay. Then when you put on the substrate likes it to be tetragonal because of the symmetry of the in-plane compressive stress. That's how we stabilize the tetragonal phase in the film. But when you grow really thick, the stress more or less relax, you're going to have those hierarchical polydomain structure of the rhombohedral ground state phase.
Okay, so let's thank the speaker and all speakers.
Thank you.